Welcome to GTC and thank you for joining us today. Before we begin, we wanted to cover a few housekeeping items. At the bottom of your screen are multiple application widgets you can use. All the windows on your screen are resizable and movable. If you have any questions during the webcast, you can submit them through the Q&A window to the right of the slides, and we will try to answer these at the end of the event. A copy of today's slide deck will be available in the GTC session catalog. You can find additional answers to some common technical issues located in the Help widget at the bottom of your screen. An on-demand version of the webcast will be available approximately 1 hour after the webcast and can be accessed in the session catalog. Now, without further ado, we'll turn the event over to our speaker to begin the presentation.
Hey everyone, I'm Amulya Vishwanath. I lead product marketing for Vision AI tools at NVIDIA. Today I'll talk about how you can implement real-time Vision AI apps using NVIDIA DeepStream SDK. All right, let's get started. Intelligent video analytics continues to see rapid growth and adoption during COVID-19. Some of the popular applications include face mask, no mask detection, social distance protocol monitoring to regulate crowded places such as malls and airport hubs, at hospitals for patient fall detection, or even at retail stores for employee safety and to enhance in-store customer experiences. All these applications require real-time and effective video analysis from multiple IoT sensors. As you already know, cameras are one of the most used IoT sensors for these systems, and they are already installed in most of the existing infrastructures. Now let's talk about how to use these existing sensors to get rich insights. There are companies and organizations who are transforming their existing infrastructure to innovate and bring the best experiences for their consumers, employees, and communities. Every industry is going through rapid transformation to use AI for video analysis. Customers typically encounter challenges such as limited access to resources and data to build and deploy highly accurate AI. Think about this. To create an intelligent system, you need AI, and creating highly accurate and reliable AI is difficult. It's an iterative process that requires lots of good labeled data, and gathering this data is time-consuming and expensive. Not to forget, models are trained and retrained continuously. The next challenge is about the unclear production path with throughput challenges. When you deploy your AI application, you want to achieve high throughput and be able to generate real-time insights. Increasing the number of streams per device reduces overall costs for your customers. And besides AI, there are a lot of other high computing processes that are involved in video analytics. The third key challenge is with respect to deployment, not knowing how to securely deploy production-grade apps for customers. A real application deploying involves deploying and managing hundreds to tens, hundreds, or in most cases, thousands of edge deployments, and this can get challenging. Physically connecting to the edge device is not always possible, so you need a way to orchestrate and manage all your edge appliances from a central location. It's also very important to build a secure IoT connection between the edge and the cloud. You are now ready to build and deploy your vision intelligence application. I'm sure you've already wondered how to tune it to the best performance, achieve highest accuracy, or even reduce total cost of ownership. That's right. Many companies build fragmented solutions that do not provide reproducible results and accurate AI. If you think that there is a product that can help achieve good accuracy, you also need to ensure that the inferencing and real-time deployment is easy and scalable, else you slow down going to the market with your solution. As a developer, you have greater degree of flexibility with choosing the production path for your application. The three key options provided by NVIDIA's technologies and tools include: first, you can choose to use the purpose-built pre-trained models such as PeopleNet, DashCamNet, and more that are highly accurate with Transfer Learning Toolkit. Now, you must be wondering, what is Transfer Learning Toolkit? TLT or Transfer Learning Toolkit is our zero coding toolkit that helps you accelerate AI training time and deploy efficiently with DeepStream SDK. DeepStream SDK is our streaming analytics toolkit for AI-based video and image understanding. With DeepStream, you can build efficient applications that allows you to do real-time AI. The cloud-native TLT framework accelerates AI training by over 10x, as I mentioned earlier, starting with NVIDIA pre-trained models, enabling data augmentation, and network optimization like pruning in a simple operation. The second option for developers is that they can choose from DetectNet V2 or SSD or DSSD and more with ResNet VGG network architectures and quickly custom train it to your application using TLT and still deploy with DeepStream. The third option is really you can choose to build a custom model and manually train, optimize, and deploy with DeepStream. Though remember that this might be more time consuming. We recommend that for end-to-end intelligent video analytics pipeline, you use our purpose-built pre-trained models, Transfer Learning Toolkit, and DeepStream SDK. In the next few slides, I will talk more about how DeepStream SDK can be used to build and deploy intelligent video analytics apps and services. DeepStream is one SDK built for many industries. Whether you're a CTO for a startup building a retail analytics-based solution to understand consumer behavior inside a store, their sentiments to products, or even if it's an application that is used for parking guidance or smart traffic monitoring, you are looking to reduce training costs and accelerate time to market for your solution package. Even if you're a developer who's building application-specific pipelines, an expert system architect looking for quick prototyping and identifying and resolving pipeline bottlenecks, or even software partners who are extremely keen on reducing cost per channel for their customers and increasing the stream density per GPU, it's quite clear. We need to prepare for deployment of optimized AI workloads for highest performance, scalability, and reliability. In the next section, I'll give you an overview of DeepStream SDK, features you can use today to optimize your intelligent video analytics application, and some cool reference apps that can be built using DeepStream. So let's start with an overview of DeepStream SDK. DeepStream SDK, as I mentioned earlier, is our streaming analytics toolkit for AI-based video and image understanding. With DeepStream, you can build efficient edge applications that allows you to do real-time AI. This is the entire DeepStream software stack from application level to all the way down to compatible hardware. At the very top is the application layer. You have the flexibility to choose between native C++ or Python using the DeepStream Python bindings for development. Right below the application layer is the SDK. The core SDK consists of various hardware-accelerated plugins that provides the highest throughput for any computer vision and intelligent video analytics applications. There are plugins for hardware-accelerated decode, encode, and other processing tasks. Select from about 15+ existing DeepStream custom plugins or create your own. For deployment, customers can deploy their application using bare metal systems, or they can deploy in cloud-native containers using NVIDIA Container Runtime. Bidirectional IoT messaging allows the cloud to control and configure DeepStream application on the edge. Over-the-air model update allows for instantaneous model update while the application is running. In addition, we provide several reference apps and helms for container orchestration to kickstart your IVA or Intelligent Video Analytics project. The next level of the stack is CUDA Stack. This lists various software technologies that are used by DeepStream plugins. This includes libraries such as CUDA, TensorRT, TRITON Inference Server, and multimedia libraries. At the very bottom is the full hardware stack that can be used to deploy DeepStream applications. This includes NVIDIA Container Runtime and Kubernetes on GPU. DeepStream can be deployed on any NVIDIA Jetson devices or Tesla GPUs. DeepStream also offers turnkey integration with AWS IoT and Azure IoT. Now let's talk about DeepStream graph architecture. This pipeline for processing and understanding video or image is industry agnostic. It's a typical IVA pipeline constructed with DeepStream plugins. Underneath the plugins, it shows the underlying hardware that is used by each of the plugins. The first step is capturing the streaming data. This could be coming from an RTSP stream, from a file, or from a USB or CSI camera. Next is to decode the frame. Decoding is very compute intensive. Therefore, we use NVDEC, our hardware accelerated decode on NVIDIA hardware. This is different than the CUDA cores on the GPU. So you can be rest assured that the core GPU will be completely utilized for AI inferencing. After decoding the frame, there might be some pre-processing before inferencing. This could be image conversion, image scaling, cropping, or if the stream is from a 360-degree camera, then you need to dewarp the image. There are various accelerators for these operations. After image processing, you batch the streams before sending it for inference. Batching allows us to utilize the entire GPU efficiently for inferencing. After batching, you send the data for inference, which can perform object detection, classification, and segmentation. This is run on the GPU or DLA, the deep learning accelerator available on Jetson AGX Xavier or Xavier NX. After inference, you might need to track the object for insights, tracking or re-IDing cars on the road or people inside a building. Finally, the last step is the output. Here the options are you can view or store the video with the bounding boxes and labels, or send just the metadata to the cloud for further analytics. Last month, we announced availability of DeepStream 5.0 GA. Here are the key features from our latest release. We've added Python samples, and I'll talk more about the reference apps available with Python bindings in the next few slides. There's also bidirectional messaging that enables you to send metadata, monitor health and multimedia, and orchestrate apps. Over-the-air model update offers zero downtime. Smart Record enables selective event triggers for faster searchability and saves disk space. TRITON integration enables you to deploy an open source model natively from TensorFlow, TensorRT, PyTorch, or Onyx in your DeepStream pipeline. With DeepStream 5.0, you can build and deploy DeepStream apps natively using Red Hat Enterprise Linux. I'll dive deeper into some of the key features in the next few slides. Now let's spend some time looking at DeepStream Python bindings. DeepStream pipelines can be constructed using GSD Python, the GStreamer framework's Python bindings. For accessing DeepStream metadata, Python bindings are provided in the form of a compiled module, which is included in the DeepStream SDK. The DeepStream Python application uses the GSD Python API action to construct the pipeline and use probe functions to access data at various points in the pipeline. The data types are all in native C and requires a shim layer through PyBindings or NumPy to access them from the Python app. Tensor data is the raw tensor output that comes out after inference. If you are trying to detect an object, this tensor data needs to be post-processed by a parsing and clustering algorithm to create bounding boxes around the detected object. With the availability of tensor data, you can create your parsing algorithm inside the Python app. This is important because the size and dimension of the tensor data, as well as the parsing and clustering algorithm needed to parse the data, is dependent on the type of AI models. If you want to be able to bring new models or new post-processing techniques to DeepStream, you'll find this extremely useful. Another useful data source to access is image data. This can be used to capture anomalies where the AI model picks up an object and you want to save the image for future reference. Accessing this frame is now supported through the app. There are many sample apps to get started today to build DeepStream pipelines using Python. The sample apps provided here demonstrate how to work with DeepStream pipelines, and these sample apps require metadata bindings to work. To get started, use one of the reference applications provided for object detection, tracking, multi-stream 4-class object detection, image data access, RTSP input-output, USB camera input, and so on. Some of the notable apps that we are providing have the ability to save image data from the pipeline. This is useful when you want to save certain image data of interest. Now, with the Python API and sample apps, users can incorporate this feature in their own application. Let's look at the example to take streaming RTSP in and output streaming RTSP out. This is a typical use case for IDA applications where the streaming video is coming from an IP camera over RTSP and need to send it upstream to a central server or cloud. We also have several examples for you to try today, so do take a look at the Jupyter notebooks on GitHub, which makes it easier to get started today. There are several IoT features that are offered by DeepStream SDK. Let's talk about bidirectional messaging. Now imagine your application is in production. It's processing on the edge and using AI to generate some insights. It sends these insights back to the cloud. In addition, it also sends other stats such as health of the device, logs, or errors on the device. It can also transmit multimedia files such as images or videos. In the cloud, you find that the current model is not performing well under certain conditions. So you retrain the model and want to update the model on the edge. Or you may want to change some parameters on the edge application. This could be adding or removing camera sources, changing camera settings, or changing the region of interest in the application. You may also be interested in pausing, resuming, or stopping the application. For all of these activities, you need a mechanism to receive and act upon those messages on your edge application. This requires a bidirectional communication between the edge and the cloud. The bidirectional communication in DeepStream will use the Kafka message broker. With Kafka message broker, DeepStream will be able to subscribe messages from the cloud as well as publish or subscribe to multiple topics. There are several reference examples for developers to get started with bidirectional messaging. For a successful scalable deployment of IoT devices, one of the most important and overlooked aspects is security. That is, being able to securely communicate between the edge device and the cloud. Security around IoT devices is a growing concern with so much data and sometimes sensitive data generated on the edge that you want to ensure you're sending to a trusted location. With DeepStream 5.0, we support two-way TLS authentication based on SSL certificates and encrypted communication based on public key authentication. The two-way SSL authentication works with the Kafka message broker. The client certificate is generated and stored outside of DeepStream application. Secure authentication can be configured in the DeepStream app via the message broker plugin. The two-way TLS authentication is based on handshake protocol between the client and the server, as you see in the graphic on the right side. When the client is ready to communicate, it sends a request to the server. The server sees the request and sends the server certificate. Then the client verifies the server certificate with certificate authority. If successfully verified, it will present its own client certificate to the server for two-way authentication. Then the server verifies the client-side certificate with certificate authority. If successfully verified, it will acknowledge the client that a successful communication was set up. Only after secure authentication is established can the client and server begin to communicate. Now let's talk about another IoT feature, which is over-the-air model update. AI is an iterative process. Your model works best on first day of your deployment. As more and more corner cases are discovered, the AI model that you deployed will start to perform poorly on those. So you need to collect new data, retrain the model, and then deploy back in the field. This process repeats as you seek to improve the quality of the model. This continuous model update means that you need to communicate to the app running on the edge that a new model is available so as to pick that up. This is where you need the bidirectional messaging functionality to send messages from cloud to the edge. Other use case for on-the-fly model update is if you want to change models based on certain time of the day or weather conditions, because certain models might work better under certain lighting conditions. With over-the-air model updates, you can swap to a different model on the fly. Imagine a robot is doing inventory management. The robot might need a different model for each aisle because the product SKUs in each aisle are completely different. So instead of having one monolithic model, you have multiple more accurate models that needs to be swapped immediately. Over-the-air model update helps with instantly swapping the model while the application is running, resulting in zero downtime. And all of this happens without shutting down and restarting the app. This is extremely important for mission-critical applications where you cannot afford to experience any downtime. Another use case for bidirectional communication is to initiate a record based on a trigger on the edge device for certain conditions. Let's say, for example, you have a smart city application where you're tracking the direction of the cars on the road. One of the anomalies could be to monitor and flag cars going in the opposite direction. The way you have architected your design is you do car detection and tracking on the edge using DeepStream, and then you send these insights to a data center or cloud for further analytics. In the cloud, you have an anomaly detection algorithm that takes the metadata and looks for anomalies on the road, one being car going in the opposite direction. Once you detect that a car is going in the opposite direction, you immediately trigger the DeepStream application to record the event for some finite amount of time. The trigger doesn't necessarily have to come from the cloud. It could be from any other microservices running on the edge. In DeepStream 5.0, there are APIs to start and stop recording based on external triggers. The two main benefits of this feature is that with selective recording, you can now save valuable disk space. Imagine in a city with thousands of cameras, recording all the footage 24 hours is very expensive when 99.9% of the time it is not needed. Another benefit is faster searchability. When something interesting happens, instead of reviewing hundreds of hours of footage, you can quickly review few clips, which can save valuable time. Smart Record is currently supported for Kafka, and there is a sample app that can help you get started with using this feature today. With DeepStream 5.0, we've added support for NVIDIA TRITON Inference Server, formerly known as TensorRT Inference Server. TRITON Inference Server is an inference microservice originally designed for data center GPUs and now is extended to embedded line. It simplifies deploying AI inference in production environment by maximizing GPU utilization and seamlessly integrates into DevOps deployments with Docker and Kubernetes integration. TRITON Inference Server is available in a ready-to-deploy container from NGC. TRITON Server supports various deep learning frameworks such as TensorFlow, TensorFlow TRT, PyTorch, Onyx Runtime, and others. With DeepStream, users can simply use TRITON Inference Server with a simple config file change in the DeepStream app. We have released a new inference plugin that uses TRITON Inference Server. With that said, native TensorRT is still supported and is the preferred way to do inference if you're really looking for high throughput and performance. The downside is TRT can sometimes be limited due to certain layers not being supported out of the box. TRT provides custom plugin to add missing layers, but that is not always trivial. The ideal case for TensorRT is when you're ready to deploy, and we recommend converting to TensorRT for highest performance. But on the other hand, if you want flexibility of running any network out of the box with DeepStream and you're okay with some amount of performance trade-off, then Triton Inference Server is the alternative. This is usually the case when you are prototyping and are still coming up with the architecture and experimenting, and you do not want to spend time and effort converting your model to TensorRT. In this case, you can create the entire end-to-end video analytics application and use Triton Inference Server for inferencing. So in summary, you have two options to run inference now, and you can decide which ones work best with your network. There is a feature explainer blog that talks more about the native integration with Triton Inference Server. Do take a look at this developer blog. Here's a quick look into Triton DeepStream architecture. The advantages of using Triton Inference Server includes multi-GPU support. So now you can run multiple instances on multiple GPUs. As I mentioned earlier, there's a support for a wide variety of frameworks, including PyTorch, TensorFlow, Caffe2 out of the box. You could also use Triton Inference Server for custom pre-processing methods via Triton backend. With the native integration to Triton Inference Server, you can now deploy an open source model. Now let's look at a high level what it takes to deploy an open source model with DeepStream SDK and Triton Inference Server. First, you start with downloading the open source model you'd like to deploy. Let's say for this example, we'll consider a TensorFlow faster RCNN Inception v2 model, and let's use Cocoa dataset labels. Next is to create the Triton configuration file. Start with creating a model configuration file, which will include information about the input tensor to the network, the names, shapes, and data types of the output tensor nodes, and other information about the network needed by Triton. Also, you need the DeepStream reference app that requires two configuration files for this model. One is the DeepStream application config file, which sets various parameters for the reference app, and the other file is the inference config file, which sets inference-specific hyperparameters for the chosen network. Specifically, with the inference config file, you provide inputs, outputs, pre-processing, and post-processing required by the app. Next step is to build a custom parser. In order to obtain the bounding boxes from the output nodes of the network, we need to pass the output to a post-processing parser. DeepStream provides some sample parsers for bounding box detection and image classification. For this example, the output nodes are detection boxes, detection classes, detection scores, and number of detections. The final step is to run the DeepStream app to see the output. If you're interested in further working details about how to deploy an open source model, I recommend checking out our recently published tutorial on how to get started with deploying TensorFlow models using DeepStream SDK and Triton Inference Server. With DeepStream SDK, you can apply AI to streaming video and can simultaneously optimize video decode and encode, image scaling and conversion, and edge-to-cloud connectivity for complete end-to-end performance optimization. This plot summarizes stream density achieved at 1080p 30 fps across various NVIDIA platforms, including T4, Jetson Nano, AGX Xavier, and Xavier NX. You'll notice that you can achieve higher stream density overall by using DeepStream. There is an excellent video tutorial that we've put together to show best practices for performance optimizations. Do check out the video tutorial here. Now let's look at the interoperability of DeepStream and Transfer Learning Toolkit. For an end-to-end workflow from training to deployment, you start with the pre-trained models and the TLT container from NGC. Train them with your own data set using Transfer Learning Toolkit. Once trained and pruned, you export the model. Trained models from TLT will work out of the box with DeepStream, and this includes all the purpose-built pre-trained models as well as generic models in YOLO, FasterR CNN, SSD, or any other networks. These models are fully compatible with TensorRT. In DeepStream, it's a simple config file change to point to any model. Efficient training with Transfer Learning Toolkit and real-time inference with DeepStream will give you the highest possible throughput for any video analytics application and can speed up overall development time by 10x. DeepStream offers exceptional throughput for a wide variety of object detection, image classification, and instant segmentation-based AI models. To reduce development efforts and increase throughput, developers can use highly accurate pre-trained models from Transfer Learning Toolkit. These include the PeopleNet, ResNet, TrafficCamNet, DashCamNet, FaceDetect IR models from TLT, and deploy with DeepStream. The following table shows the end-to-end inference performance on 1080p 30 fps input stream. Note that running on the DLAs for Jetson Xavier NX and Jetson AGX Xavier frees up GPU for other tasks. DeepStream SDK is built for many industries and multiple use cases, and these end-to-end reference apps are a great starting point. Let's look at some of the interesting end-to-end reference apps, such as People Analytics for Crowded Spaces, Social Distancing app, and Face Mask, No Mask detection using TLT and DeepStream SDK. In the next few slides, I'll give you an overview of each of these end-to-end reference apps and additional resources on how to get started with these reference apps today. In this COVID-19 world, it's important to manage and monitor occupancy inside stores, malls, airports, and transit hubs to ensure that social distancing protocols are properly followed. The way this application works is that you take an input stream, detect count of people entering and exiting the building, and send this data to the cloud. We use PeopleNet model, Transfer Learning Toolkit, and DeepStream to create an application which counts the number of people entering and exiting the building, and then send this analytics data to cloud to monitor for further processing. There is a recent developer webinar on how to create a People Analytics app for smart spaces, which gives you detailed information on the application setup, plugins used, and step-by-step guidance on how to add custom code and run the DS app. You can find this reference application on our GitHub repo. Now let's look at a quick demo for People Analytics in crowded spaces. Another interesting DeepStream reference app is the Social Distance Monitoring System. This app is mainly used to extract metadata of people, how far they are located from one another. We will be soon open sourcing this reference app in the next few months or so. Let's look at a quick demo of the Social Distancing app. The Face Mask No Mask Detection Reference app uses Transfer Learning Toolkit and DeepStream SDK. Our approach here is to build a demo that uses two-class object detection to detect faces with masks and faces without masks. For this experiment, we chose DetectNet V2 with ResNet 18 from Transfer Learning Toolkit. We noticed significant improvement in inference performance with model pruning and accuracy as seen in the inference evaluation table here. The datasets used for this experiment are masked faces, Kaggle medical mask, wider face, FTDB, and celebrity dataset. What we provide is a Jupyter notebook, a developer tutorial, and basically a developer recipe to learn how to build with an open source dataset. You can get started today by checking out our GitHub repo and our developer tutorial. I also highly recommend checking out our GTC session on Transfer Learning Toolkit to learn more about this reference app. Let's look at the demo video for Face Mask No Mask Detection now. DeepStream SDK has seen explosive growth, and there has been tremendous worldwide adoption from our partners and customers who are building unique end-user intelligent video analytics apps and services. In summary, creating highly accurate and reliable AI is challenging. You need to reiterate and train on lots of data. With NVIDIA's Transfer Learning Toolkit and plethora of pre-trained models, you have the flexibility to choose the type of network architecture and retrain models for highest accuracy. There is a dedicated talk from one of our experts on Transfer Learning Toolkit, this GTC, that I would highly recommend. The thing that is common across all the industries implementing intelligent video analytics is you need to process pixels from camera to collect insights. The type of application might differ, but the flow from pixels to insights remains common across all the use cases. DeepStream offers the streaming analytics toolkit to efficiently process and understand video across many industries. Building an efficient pipeline to process and use AI on video streams is not trivial. There are lots of hardware-level optimizations that can help improve performance. With DeepStream SDK, we have done a lot of the heavy lifting to get you the highest channel density. With efficient memory management and hardware-accelerated plugins, you can be rest assured that you will get the maximum throughput. Finally, for at-scale deployment, you need to manage and orchestrate hundreds or thousands of edge devices from a central location or cloud. Building cloud-native applications using containers and orchestrating with Kubernetes platforms allows you to scale out. The DeepStream application can be built in cloud-native containers and deployed with Kubernetes. So go check out DeepStream SDK today to build and deploy high-throughput, low-latency, intelligent video analytics apps, and tell us what you think. Here are some important developer resources to get started with your next intelligent video analytics app. In addition, there are new blogs that get added on a monthly basis. I recommend checking those out on our developer blog website. If you have a feature request to make or want to learn more about DeepStream SDK or any of the other tools, please use developer forums to reach out to one of our experts. Be sure to check out our community projects page to learn about unique applications built by the developer community. And finally, enroll in the NVIDIA Developer Program if you haven't yet to receive the latest updates on DeepStream SDK and in general about intelligent video analytics announcements. I hope you enjoyed learning more about software tools available for implementing and deploying real-time intelligent video analytics apps. This concludes our webinar today. Thank you for joining us.
Excellent. Great presentation, Amelia. We're now going to move to the live Q&A section, answering your questions. So Amelia, I'm going to start with this first one. Is it possible to create a plugin such as GSB DS example in Python?
Thanks, Adam. Yes, you can certainly create a plugin in Python. We do not have a sample app showcasing this yet, but we will certainly consider making that available in the future DeepStream release.
Perfect. That's great. The next question is, an issue with DeepStream is that TensorRT doesn't easily support models from other architectures. Int8, for example, conversion tools are basic and not overly well documented. This makes it difficult to use DeepStream out of Jetson. Are there any plans to expand support from DeepStream for other architectures or expand TensorRT compatibility?
Yes, so this was an issue with DeepStream 4.0, but we recently launched DeepStream 5.0, which now includes native integration to TRITON Inference Server, which helps you with just that. You can now take a model from TensorFlow, TensorRT, Onyx, or PyTorch and deploy it today. There is a developer blog that highlights how to take any model and deploy it using DeepStream and TRITON Inference Server. You can take a look at that. The links are also in the presentation.
Great. The next question is, what algorithm is used for tracking in NVTracker pipeline, in the NVTracker pipeline component?
Yes, so basically there are three tracker algorithms. One is the KLT algorithm. The other one is intersection of union, which uses the intersection of a detector's bounding boxes across frames to determine the object's unique ID. And the third one is NVDCF, which uses a correlation filter-based online discriminative learning algorithm.
Okay. Next question. When using PeopleNet, can we blur faces before we save the video stream?
Yes, you can redact faces before saving the streams, and we have a blog that talks about redaction and how to do that with DeepStream. Take a look at the blog on our DeepStream Getting Started page.
Okay, and that's the within the DeepStream developer page?
Correct.
Great. Next question. Is OTA supported only for updating models or even library versions?
So currently OTA is only supported for model updates.
Okay. Another question is, where can I find face detection within DeepStream?
So the face detection developer recipe, which we showed using Transfer Learning Toolkit and DeepStream SDK, is available on GitHub. And you can also find a developer blog that highlights how to put up this workflow on our dev blogs website. It's also available on our DeepStream Getting Started developer page.
Okay, excellent. Well, Amelia, it looks like, and everyone, it looks like this is all the time we have for today. I think that's going to be the last question. If there are unanswered questions, we'll definitely try to get answers out to you via email. So thank you very much, all of you, for joining us for the session at GTC. The session will be available on demand in the session catalog in just a few hours. Have a great day, and thanks for joining us.
Thank you.